Welcome everybody. So let's look over our sample homework number 2. So I've shortened our list of rules from our packet that we did. And so here what we want to do is we want to look at nuclear stability in number 1. So we're going to be looking at the neutron to proton ratio. The first rule says if Z, the number of protons, is greater than 83, it's going to be radioactive because it doesn't fall on our belt of stability graph. 2 is a shortcut, right? If you have 2 evens or 2 odds, you can make a determination. But if you have 1 odd and 1 even, you're going to have to plot. And of course, you can always plot. If there's a point already on the BOS, you know it's stable. If there is no point that you have to add that point, you know that it's radioactive. So the first thing you're going to want to do is to take inventory of your neutrons and protons. And so I'm going to look up my elements here. So I have phosphorus, which is element 15, Sn is 10, which is element 50, and rubidium is element 37. And then I'm going to subtract my protons from my mass number, so 33 minus 15 gives me 18 neutrons. 116 minus 50 gives me 66 neutrons, and 85 minus 37 gives me 48 neutrons. And so what we see is 1 and 3 we're going to have to plot, but for number 2, we can simply say that since we have an even number of protons and an even number of neutrons, we have a stable isotope. But for phosphorus 33 and rubidium 85, we need to plot these. And so just be careful, right? So I'm going to kind of highlight a little bit here. So if I'm looking for 18 neutrons, that's those 3 dots right there. And if we want to highlight 15 protons, that's those dots right there. And so what I see then is, right, my my phosphorus 33 would fall right there. In fact, there is no point. So label, if you have to plot, label. And so here, there is no dot on the BOS. And so I know that phosphorus 33 is radioactive. Now, when we look at rubidium, again, we can kind of go in and highlight the things that have 48 neutrons. They're right below 50. It's these 3 dots right here, right in there. And we can see that that middle dot of those 3 is in fact our rubidium 85. And so in this particular case, we have a stable isotope because there is a point on the BOS. So again, make sure that you label. All right, let's move on to page 2. So here in page 2, we have a equation to balance. And so remember, when you do this, you just want to make sure that both sides of your arrow are equal. And so I've got 27 and 4, that's 31. Here I've got 13 and 2, that's 15. And so 30 plus what number is equal to 31? So that top number needs to be 1. 14 plus what number is equal to 15? The bottom number is 1. And so that's a proton, or it's a hydrogen 1 nucleus. So again, just balance the mass numbers and the atomic numbers on both sides of your arrow. So using that, let's look at number 3. It says write an equation for the decay of nickel 63. Nickel 63 is represented thusly, and it says to produce copper 63, and copper is element 29. So here you're just trying to figure out what is my missing particle. So again, my mass number hasn't changed. I have got 63 on both sides. I don't need any more. But on the bottom, I have 29, and I need to get it down to 28. So I'm going to have to put a -1 there. And so this is a beta particle. And that leads us into number 4, right? Beta particles are electrons. And so here we're looking at 2 sequential beta emissions. And so I'm going to do this step by step. So I'm going to start with my first beta. So here I have my cadmium 115. Cadmium's element 48. And so it's going to undergo a beta emission. Remember that beta particle is going to end up on the right-hand side. And so we're going to see the same thing that we saw above, right? No change in mass, but the bottom number is going to increase. In this case, it's going to increase 1 to indium 115. And then for your second beta, you're going to start with a product there. So you're going to start with your indium 115, and that's going to undergo a beta decay to yield, again, something where the mass hasn't changed. So it's still going to be 115, but the bottom number is going to increase by 1 to 50, which of course is SN, or 10. Again, you could write that all as one expression if you wanted to, where you simply take your initial cadmium, you do your beta particles, but you get 2 of them, and you're still going to end up with 10-115 as your answer. Let's go ahead and look at the bottom. And remember, there's just 2 rules here when it comes to figuring out the type of decay, right? First, is Z greater than 83? If yes, you know it's alpha. If no, you go to step 2 where you're comparing A versus AW, right? Mass number versus atomic weight. If A is bigger, it's beta. If the atomic weight is bigger, we know it's positron. And so the first thing you want to do is look up your atomic numbers, right? So silicon is 14, tungsten is 74, vanadium is 23, and plutonium is 94. And so plutonium has a Z that's greater than 83, right? The 94. And so we know that plutonium is going to be alpha. For the other ones, we want to go to the periodic table and hunt down what it says. And so I'm just going to quickly tell you, right, when you go look up silicon, it tells you it's 28.09. When you go and look up tungsten, it's going to tell you it's 183.84 on the periodic table. And when you go and look up vanadium, it's going to tell you that it's 50.94. And so now we're going to compare our mass number to that. And so here, my mass number is 32, which is bigger than the 28.09, so this is going to be beta. Likewise, my 185 is bigger than the 183.84, and so it's also beta. But for vanadium, right, my 48 is smaller. The periodic table is bigger, and so it's going to undergo positron decay. So again, all of these things were covered in our nuclear chemistry packet, so you can use that as well. And as always, thank you for your time.